Welcome to this class on defects in materials. In the last class, we have looked at the stress and strain field around a perfect screw and an edge dislocation. Okay. But generally, the dislocations are not either a perfect screw or an edge dislocation. It is a mixed dislocation. Okay. So how do we find out the stress and strain field around a mixed dislocation? We will just look at it. Okay. And all the cases which we are considering is for isotropic case, right? That isotropic elasticity is what we are considering it. Okay. Because for a screw dislocation, the displacement which is there, u equals v equals 0, only the w is going to be there, which is b by 2 pi into tan inverse y by x, correct? And epsilon y is z, epsilon x is z, these are all only the stresses which we see, and sigma y is z and sigma x is z are the stress fields which we see around the dislocation. What happens in the case of an edge dislocation? U and V exist, right? Displacement field is not equal to 0, that expressions which you had seen in the last class. W equals 0, correct? And the strains, if you look at it, epsilon xx, these are all the strain fields are there. Equals 0. And stresses, if you look at it, sigma xx, sigma yy, z, these are present. Sigma y is z, x is z equals 0, correct? This is how it is. When we look at a screw dislocation and mixed dislocation, for a mixed dislocation, okay, we assume that the way we can look at is one, we can look at the mixed dislocation as a curved one, or we can look at it that this is a straight dislocation, okay, with the line direction u, and the bias vector is inclined with respect to a dislocation. That way also we can consider it. Okay. Let us just consider this case. Then this will be BE, this is the angle theta it makes with the line direction, and this will be BS, the screw component. Okay. So BS will be equal to mod B into cos theta, BE equals into sin theta, correct? From this expression, now if you look at it, you can understand very easily that for a screw dislocation, okay, only the displacement W is there, correct, for any screw dislocation. So that means that with respect to it, for the screw component, if we are trying to find out, we will be getting expressions which are corresponding to sigma y z and sigma x z. These are all the stress components. Whereas with respect to edge component of the mixed dislocation, we are going to get the other stress components, right? These components are all independent. There is no component which is common. So what is the advantage of it? We can take with respect to this corresponding to the screw component. Only thing is that the B has to be taken as the component of BBS, okay? And here for this U and V, the edge component has to be taken. Then this can be used to describe these expressions give, okay. If you find out the stress and strain with respect to taking the component of B, the screw component or the edge component, for mixed dislocation, all the stress components could be calculated very easily, okay. Generally, what happens is dislocations are never straight. They are always like this, they will be bent like this, okay. Then they will have a Burgess vector may be in a specific direction which is defined crystallographically. So the line direction here could be in this direction, line direction here could be in this direction. So the various ways in which the line direction. Actual computation when we have to do, what are the options which we have to choose it? One which we can do it is, you take a small segment of this to be the dislocation line, correct? And with respect to this, we can find out the screw and the edge component and do the calculation, correct? Other is, way of looking at it is that this itself can be considered as a screw, okay. This is the way, that is dislocations will have, one will have a B, that is a screw component and an edge component. The dislocation line itself can be, that is, if a dislocation is bent like this, we can assume it to be like this, a small, like this we can take it, okay. And if the Burgess vector is in this direction, then this will be a screw component of this dislocation, and this will be the edge component. Depending upon that, here if we come in, the edge component will become more, the screw component will become less, that length will vary. This way also we can look at it. Both the options are available for computationally determining the stress field and strain field around a mixed dislocation. That is, to do that we have to split them into screw component and edge component, okay. Either we take the line direction to be the same, take the Burgess component, or keep the Burgess component, Burgess vector the same, and the line itself can be taken to be an edge and a screw, okay. Both options are available. Okay. With this, we have got expression for the stress field and the strain field around a dislocation. When we know the stress field and the strain field around a dislocation, we can calculate the total energy which is associated with introducing dislocation in the sample, correct? So if you look at the dislocation energy, in doing that we have to keep one point in mind, that here also when we have calculated the stress field, the core of the dislocation has been omitted, because where the elasticity theory is not, we cannot apply the elasticity theory. Okay. If you have to find out the strain energy of the dislocation, how do we go about and do it? Okay. We know that if we take any material, okay, the linear elasticity theory, we apply it to find out the strain energy, okay. That is, the Hooke's law is, we can apply it, and all these expressions are given here, okay. That is, if by applying some stress, okay, a small increment in strain is introduced into the sample, okay, what will be the total increase in internal energy which will be taking place in the material because of this strain? This we can write it as sigma into d epsilon, which we can write it. Anyway, in the view graph I had given with respect to a tensor notation, here I am just writing it as this, I can write it as epsilon ij. Okay. What we are doing it is, we assume that it's only this component is being applied in only one direction. Okay. That's a small increment. If the total strain, okay, changes from 0 to some particular value, take it to be epsilon ij. Then if we integrate this, we can find out epsilon ij, correct? This itself can be written as, the stress can be written as Cij, okay, epsilon ij, dij, d epsilon ij, correct? This way we can write it. This will turn out to be, Cij can, finally it will turn out to be half Cij epsilon ij squared it will turn. This will be nothing but half sigma ij epsilon ij, correct? This is how. Okay. Now we know that we know that the stress and strains are tensors. There are 9 components associated with it. Okay. If we take a small volume of a crystal, okay, and then apply some displacement, that will result in stresses and strains, okay, then the total increase in energy is given by this formula, W equals half into all the components. Here the twice which it has been taken because we know that the stress and strains 9 components are going to be there, okay. So these components get repeated, that is why twice it comes. So now if you look at it, total 9 will be there, okay. Using Hooke's law, we can write the same expression in terms of either strain or in terms of stress, correct? So if we write it in terms of strain, okay, then this expression turns out to be in terms of lambda and g, okay. This is the way the expression turns out to be. And if it write in terms of stress only, then also this equation turns out to be, okay, some square terms of stress, okay, and then some product terms. But in both the cases, if you can see, we can see that essentially it is strain squared will be coming in all the terms, okay, or the product of 2 strains are there, that is equivalent if they are the same, it is to be square term, okay. That is how these values turn out to be, okay. This is what a general expression when all the components of the stress and strains are present. Now we have looked at a dislocation where it has a stress and strains are present around a dislocation, but we know only a few components are there. Then we can find out what will be the strain and the stress, okay, around the dislocation, okay. Then whatever the components which are there, we can substitute it and find out what is the total energy which is generated in the sample due to the creation of a dislocation in the material, okay. Here again, when we consider the strain energy of a, or this energy could be called as a strain energy which is generated in the material due to dislocation, or this is called also as the self energy of the dislocation, okay. Both the terms are being used to represent this energy, okay. The total energy now it consists of 2 terms. One is called as the core elastic. That is, core is the region where we cannot apply the Hooke's law, okay. Linear elasticity theory cannot be applied, okay. So if we look at it, the stress and strains what we had calculated is also outside of the core, okay. This will give rise to the elastic displacement, okay. This part of the core energy, okay, this tells about how the energy is varying within that small core where the displacements are very large, okay. Generally this energy has been seen to be rather very small, the core energy, okay. But what is essentially important is that this core energy can change as a function of position as the dislocation moves in the material. Okay. This is what is responsible for lattice friction stress, because we see that the friction stress varies as the one atom moves over the other, like a sinusoidal wave that happens in the case of a core energy. Okay. How do we calculate that elastic energy? Let us take the case of a screw dislocation, which is very easy to do. In the case of a screw dislocation, essentially around the dislocation, okay, if we choose a coordinate system x, y, z, budget vector b is in this direction. Okay. So at a distance r from the core of the dislocation, okay, if you look at it, the stress field which is present is sigma yz and sigma xz, correct? These are all the only two stress fields which are present. So what will be the total energy that we can calculate in this formula? If you see that all other terms turn out to be 0, it is only this term which is going to be there, sigma y squared plus sigma xz squared, right? That is what essentially is calculated here, okay, taking the appropriate expression. Okay. This turns out to be Gb by 2 pi the whole square. Okay, this is 1 by r squared, correct? Is equal sigma x z squared plus sigma yz squared. Okay. What this tells? This tells the energy at a distance r, what is the total energy. Suppose we wanted to know the total strain energy. We know that the displacement is taking place. Suppose we take a material like this. A dislocation line is being present like this one. So throughout the sample displacement is there. Now we have to calculate what is the total energy, strain energy at every point on that sample, and add them together, then only we get the total energy. Okay. That in this case, this we can take it to be of circumference 2 pi r, okay, into a small distance dr. This is the increase in area. Then what we can do it is we can integrate it, okay, this into dr, and the integrand from phi b, okay, to r, which is the outermost radius of the sample. Okay. When we do this, this value will turn out to be Gb squared by 4 pi, okay, into logarithm of r by phi b. Okay. This phi b we have chosen because we said that that's the maximum size of the core radius. Depending upon what the value is, we have to choose that appropriate value. Okay. So now what we have got, it is an expression for the total strain energy which a dislocation is introduced in the sample, or what the same which we call it as the self energy of the dislocation, that by introducing a dislocation, what is the energy which increase which has taken place in the material. Similar expression we can get it for, this is for screw. For H dislocation, if we do it, this will turn out to be though a similar methodology we can try to adopt for an H dislocation, but it's much more complicated. There are many, but finally the expressions are essentially the similar. Only thing is that 1 minus nu comes in the bottom. Okay. Looking at this expression, there are some few points which become very clear. That is, value of nu, the Poisson's ratio is around 1 by 3. If you take this value and put it, then what is essentially is going to happen is that the strain energy of screw dislocation is less than that of an edge dislocation. That is because here it will be, that is W edge will be equal to GB squared by 4 pi. This nu equals, this will turn out to be 3 by 2, correct? Maybe. If we compare this expression with this expression, we find that edge dislocation has got a self energy which is much higher than that of a screw dislocation, right? Is this clear? What will be the consequence of that? Suppose we have a dislocation which is a mixed dislocation, okay? The dislocation will always try to reach a configuration which is a screw configuration so that the energy is less, correct? That is one. What is another consequence of this formula? Suppose I take a edge dislocation, screw dislocation, I apply a stress and try to bend it, then what happens? There will be an increase in energy. So it is very difficult to bend a screw dislocation. Suppose I take an edge dislocation, I try to bend it, then what's going to happen? It develops a screw component, energy gets lowered. So it is very easy to bend a edge dislocation. Bending a screw dislocation is very difficult, but energy of screw dislocation is very small. The self energy of an edge dislocation is high. You understand that? So these consequences you can understand that from the self energy itself. These are all the consequences of having different self energy for screw and an edge dislocation. As I mentioned earlier, the core energy of this dislocation, screw or an edge dislocation, the core energy is rather a constant value, which is a small fraction, maybe less than 10% of the total energy of the dislocation. And here, when we have a dislocation which is present in a sample, okay, how do we calculate the core energy with respect to the total, not the core energy, the elastic strain energy or the self energy of the dislocation? We find out around the radius r, which is in this particular case up to the end of the sample we have to do the calculation. Since this term which corresponds to the distance comes in a log scale, if it changes from r equals 1 to 100 or r equals 10 to 100, the value will be, this value can turn out to be from 1 to possibly 2 maximum, correct? So it's on a log scale only the increase is going to take place. Because of that, we find that changes are not much as the large volumes are being taken. Okay, that's one. Another factor also which we have to take it is that since it doesn't increase very largely, okay, we can assume it to be in many cases to be equal to some constant value. Generally it is approximated to the equals alpha GB squared, this sort of an expression which is being used, where this value of alpha can change from 0.5 to 1, okay, because the rest of the terms are assumed to be not much of a change which we can, this is an approximation only, okay. Is it clear? If you try to look at what will be the self energy of a mixed dislocation, okay, then we can take, because as we have seen that since the displacement fields are different in these two cases, we can find out the components separately and add them together for the screw and the edge component, then we get the expression corresponding to the self energy of a edge dislocation, of a mixed dislocation. Okay. But we know that the dislocations need not exist at screw or an edge or a mixed dislocation, but sometimes they can be in the form of a loop as well, correct? In the case of a loop also, okay, the expression for the elastic, the self energy, the contribution to self energy from the elastic displacement is given by this formula, GB squared by 4 pi into log R by phi b. Okay. But essentially, the stress field decreases much more rapidly in a screw dislocation than in the case of an edge dislocation. Here, what is R? This R is nothing but the radius of the loop. It is not the dimension of the sample which you have chosen. Okay. So that's the only difference which one has to understand that. And the consequence of this formula approximating to this value is generally used to find out whether a dislocation reaction will occur or not. Okay. Suppose a dislocation has got a Budges vector B1, another has got a Budges vector B2. Okay. Assume that they interact and produce a dislocation which is B3. Okay. That is whether B1 plus B3 this reaction will occur or not. Okay. How do we decide? Is that if it is in the same material, G remains that same, we can find out the B squared value. Okay. So add them together, so it will be B1 squared plus B2 squared, whether it is less than B3 squared. If that is the case, then the reaction is possible. This approximation this is what we use, the rule to find out whether a dislocation reaction is going to occur or not. But this essentially comes from this condition, that is what happens to the self energy of a dislocation. So far what we have considered in these cases is essentially with respect to only a single dislocation, all these formula, correct? And here we talked about the 2 dislocations are present or 3 dislocations are present, right? So if more dislocations are present, how do we calculate the self energy of the dislocation? Then we have to define this radius r. So what is generally taken is that if many large quantity of dislocations are present in the sample, then what we do it is that find out the average distance between the dislocations, separation between the dislocations, take half of this to be the r. That is how this self energy is calculated. Quite often what it can happen is that some of the dislocations can have positive and some can have negative, but producing all of them, the energy has to be that same, correct? We will come to later, some of this depending upon the nature of the force, some of these dislocations can interact and annihilate. These aspects we will consider in the later classes. Okay. So from this we can understand that there is an energy, and this energy whatever we have calculated, derived all these expressions, okay, are for per unit length of the dislocation, right? Is it clear? Okay. This same self energy is used to represent another important property associated with the dislocation, which we call it as a line tension. Like I mentioned that if I take an edge dislocation, we try to bend it. When we try to bend it, there can be an increase in the dislocation line length. Correspondingly, an increase in energy can take place. Okay. So essentially, then we can write the force can be defined at dx, correct? The increase in length we can write it, this force. This is per unit length. If you take it, what it happens, increase in energy per unit length. This turns out to be the force, or which you call it as a line tension, like a soap bubble. When we take it, it has some area associated with it, it will like to shrink. So the same energy which we use it as the surface energy of the bubble itself, we try to use it to represent the force also, line as surface tension also, correct? The same thing which is being done in the case of a dislocation, okay? And the line tension is defined as the increase in energy per unit length of the dislocation. That means that the same expression can be considered as a force, correct? How we can do that per a unit length if you take it? This is a constant value. This term, if we try to look at it, what it turns out to be? This is nothing but a force, na? Dimensionally it is a force, correct? So that way also we can understand that it represents a force. That G is a Newton per meter squared into that B squared you put it, so it becomes dimensionally a force, right? 1 minus nu it has to be. That was put as nu. Suddenly now I find that I think in that symbol something has happened, it's put as a question mark. What I have written was, that I'll have to correct it, I will do that, okay. So what is the consequence of a line tension? We know that the line tension is similar to, suppose we have a thread which for drying cloths we put it on home. When we put a cloth on it, what happens to a wire? Because the line tension increase, it just drops down, okay. Exactly a similar thing will happen with respect to a dislocation. So we assume that a dislocation is bent into, okay. It's T, and if we take the tangent which is going to be T sin theta, okay, here also T is the line tension, the tangent to it which will come to a line is T sin theta, it is going to be, okay. And this force, if we look at it, sin theta, is the one which will be together 2T sin theta. When theta equals small, this will be, this turns out to be T d theta, okay. This you can see it in the transparency also, okay. This will be giving rise to a force downwards, correct? This T sin theta, the sign, if you look at it, the component, it is going to come down. If this dislocation has to be kept in that position, in equilibrium position, that means there should be an opposite force which should act to keep that in that position, otherwise it will be continuously bending, correct? That's right. The other way we can look at it is that what will be this force which can keep it in equilibrium? That means that if a dislocation is bent like this, and if this dislocation, you assume that a small work is being done on this dislocation, the dislocation line is trying to move in that opposite direction, okay. What will be the force which we have to apply? That we can calculate it. That is because if a dislocation moves from here, a unit length of a dislocation by a small distance, delta S, okay, if it moves, then for that the stress which is applied is tau, you consider it. The stress into the area will give you the force. That force moves every atom by a distance when a dislocation moves by a Bajs vector, correct? So the total work done in that case will be equal to tau into B into, okay, the length of the dislocation, if a unit length which is being moved, okay. correct? And this, if we take it, F will be equal to, okay, the rate of change, correct? It will turn out to be tau B, right? So this is the sort of a force that we do not know what that tau is, but that force should be equal and opposite force should be applied in this direction so that this will be in equilibrium, correct? In that bend condition. Okay. Then we can equate these, okay. Okay. When we equate all these terms, this will be turning out to be T, okay. What is T? Alpha into GB squared, we can write it. Okay. So tau will be, this is the energy, this energy should be equal to, okay, T into d theta, okay. This is what the energy balance will be, okay. Then what this will turn out to be, d theta by dl will turn out to be r, the radius of curvature, correct. So this will turn out to be r, it will turn out to be. So now we have got an expression, okay, which is essentially the tau equals, okay, GB by R, okay. This expression, where do we use it? In the case of a Frank-Reed source, okay. R in the case of an H dislocation, or in the case of a over-one looping, where we have a critical radius where the loop will form. There also this expression which we use it to find out what is going to be the stress and critical stress which is required for loop to form, correct. So far we have considered both these cases, okay. Essentially the line tension and the self energy of a dislocation. What are possible applications, okay. These cases we will consider later when we come to about the different types of sources for dislocation generation in the material and the interaction of a dislocation with the second phase particles, okay. Then we will talk about how this expression is being used, okay. We will stop here. Tomorrow what we will do it is, we will be using the next class, okay. We will talking about the forces which will be operating on the dislocation. What are the types of forces which, okay. That is a very elegant method in which these forces could be calculated. That is called as the Peach-Coiler force. That aspect of it we will discuss in the next class. We will stop here now, okay.